everybody. In this video, we're looking at crashing. Now that is a difficult part of the general maths course, often the last thing that's taught. So you can kind of think of it as the summit of the general maths mountain, where you're putting together all of this stuff you've learned about networks. And yeah, so here's what we're going to do, the learning objectives for this lesson. Let's talk about what crashing is. So it's the process of shortening the length of time for a particular activity so that you can overall shorten the length of time for a project. So you might have to shorten a few tasks so that you can overall make the project happen quicker. And, so this is, you might be doing this in practice by, if you think you've got a construction site, you bring on more employees, more people to help you do your construction. And that's going to cost you more money. And so with our crashing, what we're trying to do is we're trying to not only speed up our project, but spend the least amount of money doing it. Now, I think a better term would be expediting, kind of speeding up your project, right? But crashing is the term that project managers use. So that's what we're going to use. And it's the word used in the study design. Okay. Crashing, I think a good way to learn it is by doing an example. This is an old exam question, and we'll do that, and hopefully this will kind of tease out a few of the key ideas in crashing, and then I've got a little summary on the end that perhaps you could add to your band reference. So let's have a look. In this question, we're told that we've got some tourism information, and we're changing it, and there's 9 tasks involved. So, and they're shown in this directed network below. And we've got the duration time in hours shown on our network. So we need the minimum time in hours for the makeover to be completed. Okay, so how are we going to do that? Well, we've got to do what we did in scheduling. That is draw in, all these boxes, and we're going to put in the ESTs, and we need to find the final EST if we're going to get the time for the project to be completed. So just drawing my last kind of boxes, a bit hard to kind of fit them in here, but we'll do our best. So from the start, right, the EST is 0. And then the only way to get here is going across A, which will cost us a time of 5. Same with B here, cost us 5. Now, here we could either go, going down here, I suppose that's the only way, isn't it? So we'll call that 9. I just clean that up a bit, not such a good box. Going on the top, what do we got? 5 plus 5 is 10. But we do have a different way of getting there. So I'm just going to draw that box a bit bigger. So this way would be 9. Now, either to get to this point, we could either go 5 here and that's 10. We could go along the bottom and that would be 9 plus 5, 14. Now, when we're doing our forward scanning, we need to pick the biggest one. So we will take that 9 plus 5, 14 and put it above this vertex. Down the bottom, so plus 3 is 17. Just clean up those boxes a little bit. What are we doing on the bottom? So on the bottom, we have got, 5 plus 2 is 7. So on the bottom, we'll just put in 7. Not many ways to get hit there. Okay, now, so this G was worth 3. So it could be 17, or going from here, it could be 11, 7 plus 4. But we want the bigger one when we're forward scanning, so it's 17. And then that final J is 7, so 17 plus 7, that would be 24. Okay, and yeah, no other way to get there, so that is our biggest one. So the minimum time to complete it is 24 hours. Okay, now we need the critical path. So to do the critical path, best to probably put in the LSTs, the latest start times. So the way to do that is first we put in this final box, just whatever that EST was, so 24, and then we're going subtracting. Now it might be a bit hard to read, but this is supposed to be a 17. I might just try and clean it up a little. My little slide letting me down here. So it's supposed to be a 17. Hopefully we can all read that. So anyway, if you take 7 away from 24, you will get 17. Now going up the top, we're taking away 3, so we get 14. Down the bottom, we're taking away 4. What would we get? 13. Taking away 2, we would get 11. Going down here, we're taking away 5, so that would be 9. Going along the top here, taking away 5, would give us 9 as well, but we could alternatively go along this bottom way and we do 9 take 4 and that'll be 5. So we'll take the smallest one when we're backward scanning. Taking away 5 here would be 0, or we could take away 5 from 11 and that'll give us a bigger number than 0. So we're just going to put 0 in here. Okay, so the critical path is where all the ESTs and LSTs, the numbers in our boxes, are the same, where there's no float time. So the way to do that is to go here and then down here, and then here, and then here, and then here. So I'm just writing it out as the sequence of edges. So A, E, F, G, J. And we've got our critical path. Okay, now we're told the supervisor learns that she can employ extra staff to complete the makeover sooner. Activities B, D, E, F, and H can be reduced by a maximum of 3 hours each. The cost of reducing the time of each activity is 45. So all that other stuff that we were doing was really just scheduling. We're actually doing some crashing here because we're speeding up some of our activities. Now we're told what is the number of hours that the project will now take. Okay, what I like to do for these is draw a table, and in my table, I'm going to put the possible paths to the end. I'm going to put their durations without crashing. And then we're going to put their durations with crashing. I'm just going to write duration crashed. So our paths to the end. So first we've got our critical path, right? Which is A, E, F, G, J. But we actually need all the paths. So an alternative path would go along the top there. So A, D, G, J. And another path, and then the only other path is going down the bottom. So that is B, C, H, J. Okay, so those durations, let's work out all those durations. So the top one, we know the critical path was 24. Going A, D, G, J, we're going 5 plus 5 plus 3 plus 7. So that's 10 plus 3 is 17 plus 7 is 20. And then on the bottom, we've got 5 plus 2, 6 plus 4 is 10, plus 7 is 17. Okay, so this, without any crashing, those are our possible ways. And so our longest one is going to be our critical path. But now we can do some crashing. And so we got to take note of what can be crashed. So maximum 3 hours each of all these guys. So what I'm going to do is, normally I would kind of highlight them or maybe color them in a different color. I'm going to try and just circle them. Hopefully it won't get too messy. So things that can be crashed. So F can be crashed, and E can be crashed, and D can be crashed. And then down here, B can be crashed, and H can be crashed. Okay, have I missed any? I don't think so. Okay. Okay, so with this duration crashed, what I normally do is I actually look at the kind of maximum amount of crashing. So here there's 2 of these that can be crashed, a maximum of 3. So really we can do kind of 24 take 6 because there's 2 of them, maximum crashing of 3 each. So if you take away 6 from that, you're going to get 18. This one only has 1 that can be crashed, so we're doing 20 take 3 and we get 17. And then this one can be crashed 6 as well, so doing 17 take 6 gives me 11. Okay. So with the maximum crashing, even if we paid all of these people to work for us and do all this extra work, the quickest we could get our project done is the 18 hours, because that's still the longest part. So it'll still be our critical path. And yeah, that's the most the best we can do. Yeah. Now it tells us determine the minimum additional cost of completing the makeover in this reduced time. So what we want to do is we want to have everything done in this 18 hours, but there's no point, say, up here, bringing this path down to 11 because it's already on 17. So we actually, B and H don't need to be paid. We don't need to employ these extra people to speed up our project. So we won't bother with them. The only things we want to speed up, well, we need to do all the maximum amount of crashing for the top. So we're going to do, our crashing cost. We're going to reduce E by 3 and F by 3. We want both of those. Now with this other one, there's no point getting it down to 17. We only want to get it down to 18, so it's the same as that other critical path. So we're going to also reduce D by 2. that'll make that path 18, and that'll be as quick as we can go. And so we'll have two critical paths there of equal length 18. So that's how long our project will go for. So in terms of cost, right, it's 45 per hour, and we're paying for 3 plus 3 plus 2 hours. So that's what, 8 hours. So we're doing 8 times 45. And then so I'd maybe just chuck that in my CAS, do my 8 times 45, and I would get 360. So here's some working out I did with some explanation. So if you'd want to pause the video and read through that, you're welcome to. But yeah, so it would cost us overall $360 to do all that crashing, speed up our project to be done in 18 hours. Okay, that is my explanation of crashing with an example. Here is my summary. So yeah, this is the kind of thing that I would probably be putting in my bound reference. And just, yeah, a little summary of how to do a crashing problem. I don't think they get too much harder than that example before. So, you know, if you feel confident that you can do something like that, I would definitely recommend practicing some of these. But yeah, I think they're tricky, but certainly not impossible. So give it some good practice and I'm sure you can get there. All right, thanks for that.